There is a planet at the edge of our solar system that we have visited exactly once. A single spacecraft flew past it for less than 6 hours, snapped a few photographs, and then kept going. That was in 1986. And in the nearly 4 decades since, not one probe, not one orbiter, not one lander has gone back. We have spent more time studying the moon of another planet than we have studying this entire world, and that world is Uranus. Now, you might think the reason we have ignored Uranus for so long is simply a matter of distance. It is incredibly far away. It takes sunlight roughly 2.5 hours just to reach it. A spacecraft traveling there from Earth would need anywhere from 9 to 13 years depending on the trajectory. So sure, distance is part of the story. But distance alone does not explain what happened between the European Space Agency and Uranus over the last 2 decades. Because the real story here is not just about a planet being overlooked. It is about a decision that was made, reversed, debated, delayed, and ultimately restarted in one of the strangest behind-the-scenes dramas in modern space exploration history. And if you want to understand why that matters, you first have to understand what Uranus actually is. Because just like Jupiter, almost everything the average person thinks they know about this planet is either incomplete, outdated, or just plain wrong. Stick with me here, because this gets genuinely strange, and if you find yourself wanting to know more about the hidden corners of our solar system after this, consider subscribing. This is exactly the kind of story we dig into. Let's start from the beginning. Uranus was discovered in 1781 by an astronomer named William Herschel. He was using a homemade telescope in his garden in Bath, England, and he noticed an object that moved differently than the stars around it. At first, he thought it was a comet, but after months of observation, it became clear that this was something else entirely, something big, something in orbit. It was the first planet ever discovered with a telescope, and it doubled the known size of the solar system overnight. Herschel wanted to name it Georgium Sidus, which is Latin for George's star, in honor of King George III, who was his patron. The rest of the scientific community had other ideas. After some debate, they settled on Uranus, following the tradition of naming planets after Roman and Greek gods. Uranus was the ancient god of the sky, the father of Saturn, and the grandfather of Jupiter. So in terms of mythology, the naming actually makes a lot of sense. The planet sitting at the edge of everything, older than everything, is named for the primordial god who came before all the others. Now, for the first 150 or so years after its discovery, Uranus was mostly just a curiosity. Astronomers could see it was a pale blue-green disk through their telescopes. They catalogued its moons. They noticed its rings, which were not confirmed until 1977, more than a century and a half after the planet itself was found. But no one had any real idea what was going on down there beneath that hazy, featureless surface. And then Voyager 2 arrived. On January 24, 1986, NASA's Voyager 2 spacecraft made its closest approach to Uranus, passing within about 81,000 kilometers of the cloud tops. It was moving at roughly 64,000 kilometers per hour, which meant the entire flyby was over in a matter of hours. In that brief window, the probe captured thousands of images, detected magnetic fields, sampled the atmosphere, and discovered 10 previously unknown moons and 2 new rings. For a few hours in January 1986, Uranus went from being a blurry blue-green dot to being an actual place. A world with weather and magnetism and moons and structure and mystery. And then Voyager 2 kept going. It had to. It was never designed to stop. It was on a grand tour of the outer solar system, and it still had Neptune to visit before it left the solar system entirely. There was no going back. What Voyager 2 found at Uranus raised far more questions than it answered. The planet is tilted on its side, not slightly tilted the way Earth is tilted at about 23 degrees. Uranus is tilted at about 98 degrees, which means it essentially rolls around the sun on its side like a bowling ball. Its north and south poles point roughly toward the sun at different points in its orbit. One pole gets 42 years of continuous sunlight, while the other gets 42 years of complete darkness. Scientists had never seen anything like it in the entire solar system, and no one could fully explain how it got that way. The magnetic field was another puzzle. Voyager 2 found that Uranus has a powerful magnetic field, which you might expect from a planet that large. But the orientation of the field was bizarre. On Earth, the magnetic poles are roughly aligned with the geographic poles. On Uranus, the magnetic axis is tilted at about 60 degrees from the rotational axis, and it does not even pass through the center of the planet. It is offset, like someone grabbed the magnetic field and dragged it to one side. This kind of configuration had never been observed before. Scientists were baffled. Then there was the heat problem, or more accurately, the lack of heat. Most of the giant planets in the outer solar system radiate more energy out into space than they receive from the sun. Jupiter radiates about twice as much. Saturn radiates about 1.8 times as much. Neptune radiates about 2.6 times as much. But Uranus radiates almost exactly as much energy as it receives from the sun and nothing more. It has essentially no internal heat source, or at least not one we can detect. For a planet of its size, that is profoundly strange. Something happened to Uranus that appears to have robbed it of its internal heat, and again, no one fully understands why. All of this is what Voyager 2 left behind. A list of questions with no answers and no follow-up mission in sight. So why did it take so long? To understand the ESA situation specifically, you need to understand how space agency mission planning actually works, because it is nothing like what most people imagine. It is not a group of excited scientists sitting around a whiteboard writing down cool things they want to do and then going to do them. It is a brutally competitive, heavily bureaucratic, decade-long process in which hundreds of mission proposals compete for a handful of funding slots, and most of them never make it. At NASA, the process is organized around something called the Planetary Science Decadal Survey, which is a document produced every 10 years by the National Academies of Sciences. It gathers input from hundreds of planetary scientists across the country and produces a ranked list of priority missions for the coming decade. If your mission is at the top of that list, you have a real shot at getting funded. If it is not, you are probably going to wait at least another decade before you even get to make your case again. At the European Space Agency, the process is a little different, but equally competitive. ESA runs what it calls cosmic vision programs, which are planning cycles that define science objectives for a roughly 10-year window. Within each cosmic vision cycle, mission proposals compete for classification as either small, medium, or large missions. Large missions, which are the flagship-class missions capable of reaching the outer solar system, are the most expensive and the most coveted. In a given cosmic vision cycle, only a handful of large mission slots are available, usually 2 or 3. And here is where the Uranus story really begins. In the early 2000s, as ESA was defining its Cosmic Vision 2015 to 2025 program, a group of European scientists began pushing for a dedicated outer planet mission. They had been watching the data from Voyager 2 sit largely unanalyzed for nearly 20 years. They knew there was an extraordinary scientific opportunity at Uranus. They began drawing up the first serious concept for a European probe to the 7th planet. The concept they developed was called Uranus Pathfinder. It was proposed in 2010 as part of ESA's call for medium-class missions in its Cosmic Vision program. The idea was relatively modest compared to some proposed missions. A single orbiter, no atmospheric probe, designed to spend several years in orbit around Uranus, studying the planet, its rings, and its system of moons, in far more detail than the Voyager 2 flyby ever could. The science case was compelling. The cost estimate was within the medium-class budget envelope. The team behind it was enthusiastic and well-qualified, and ESA said no. Not because the science was bad, not because the team was unqualified. The primary reason given was cost and technical complexity. Getting a spacecraft to Uranus requires an enormous amount of propellant for orbital insertion, because you are not just flying past, you are slowing down enough to be captured by the planet's gravity. Doing that on a medium-class mission budget was considered too risky. There were concerns about whether the power systems could survive the journey. There were questions about the communication delays involved in operating a spacecraft so far from Earth. And crucially, there were other missions competing for those same funding slots that were considered more mature and more technically ready. So Uranus Pathfinder was rejected. The scientists who had worked on it were disappointed, but not entirely surprised. Getting rejected on the first try is essentially normal in this business. The plan was to refine the proposal, address the technical concerns, and try again in the next cosmic vision cycle. But then something shifted. Around the same time that ESA was rejecting Uranus Pathfinder, the scientific community's interest in a class of planets called ice giants was growing rapidly. Uranus and Neptune are not quite like Jupiter and Saturn. They are smaller, they have different compositions, and there is growing evidence that planets like them are actually among the most common types of planets in the entire galaxy. When astronomers started discovering planets around other stars in large numbers, they found that the most frequent planet size was somewhere between Earth and Neptune. Not the huge gas giants, not small rocky worlds, something in between, something like an ice giant. This matters enormously because it means that if we want to understand the most common type of planet in the universe, we need to understand Uranus and Neptune. And we understand them almost not at all. This realization began to change the conversation in planetary science circles. A mission to an ice giant was no longer just a nice addition to the list of things we would get around to eventually. It started to look like a fundamental scientific priority. In 2017, a major report from the European science community called the ESA Senior Survey Committee report explicitly identified ice giant exploration as a top-tier scientific objective. It noted that the community had essentially given up too quickly on Uranus Pathfinder and that the concept deserved to be revived and strengthened. And then, in 2022, the American planetary science community made an announcement that changed the entire landscape. NASA's Planetary Science Decadal Survey for 2023 to 2032 was released, and at the very top of its list of recommended flagship missions was a Uranus orbiter and probe. Not a flyby, not a medium-class orbiter, a full flagship-class mission, the most expensive and capable category, with an atmospheric entry probe included to directly sample the planet's interior. The survey called it the highest priority large mission of the decade. This was a historic moment. It was the first time in the history of American planetary science planning that a mission to Uranus had been recommended as the top priority flagship mission. For decades, the outer solar system priority list had been dominated by Jupiter and Saturn and their fascinating moons. Uranus had always been the afterthought at the far end of the line. Now it was first. And this is where the story gets interesting for ESA, because this is precisely where the European agency had to make a decision. When NASA identifies a flagship mission as its top priority, it often looks for international partners. The Cassini mission to Saturn was a joint NASA-ESA-ASI effort. The James Webb Space Telescope was a joint NASA-ESA-CSA mission. The Mars Express orbiter was ESA's own mission, but drew on expertise and cooperation with NASA. Big outer solar system missions are almost always collaborative to some degree, because they are simply too expensive and too technically demanding for any single agency to do alone. So when the Decadal Survey elevated Uranus to the top of the American priority list, ESA found itself in a position it had not been in before. There was now a very real prospect of a joint ESA-NASA-Uranus mission, which would change the cost calculation for Europe dramatically. Instead of shouldering the full burden of a mission by itself, ESA could potentially contribute specific instruments, or a dedicated probe, or a spacecraft component, and get a seat at the table for a fraction of the full mission cost. But here is the complication. ESA was already deep into its own long-term planning. The Cosmic Vision 2015 to 2025 cycle had already committed to its large missions. The follow-on program, called Voyage 2050, which defines ESA's strategic priorities through the 2050s, was in the process of being finalized. And the ice giants, specifically Uranus, had been identified in the Voyage 2050 plan as a priority exploration theme. But identified as a priority and actually having a concrete mission are two very different things. What happened over the following 2 years was a complex negotiation between what the scientists wanted, what the funding reality allowed, and what a potential partnership with NASA could look like. Here is the part that often gets lost in the news coverage of all this. ESA never fully walked away from Uranus. Even after rejecting Uranus Pathfinder, European scientists kept working on the concept. They published papers, they refined the orbital mechanics, they proposed instrument packages, they ran workshops. The scientific community in Europe never stopped wanting to go to Uranus. What changed over those 12 years was not the desire. What changed was the context in which that desire could finally be acted upon. And that context was provided almost entirely by the 2022 Decadal Survey. Think of it this way. Imagine you have been trying to get your city to build a new park in your neighborhood for years. You have submitted proposals. You have been to city council meetings. You have gotten turned down twice. And then one day, the federal government announces that it is making urban green space a national priority and will co-fund local park projects. Suddenly, your proposal, which had not changed in substance at all, goes from being an uphill battle to being exactly the kind of project the council is looking for. That is roughly what happened here. Now, there is something even more specific happening beneath the surface of all this that is worth understanding, because it gets to the heart of why Uranus is such a compelling scientific target. The more we learn about what Uranus is made of, the weirder it gets. We know that Uranus is classified as an ice giant, but the word ice in that classification is a bit misleading. When planetary scientists say ice, they do not mean frozen water exactly. They mean a class of compounds, primarily water, methane, and ammonia, that exist in a state that is neither quite a gas nor quite a solid. Under the extreme temperatures and pressures inside Uranus, these compounds exist in what is often described as a hot, dense fluid. Imagine water that is under so much pressure that it cannot expand into a gas, but is so hot that it cannot quite solidify into ice either. It is a strange, in-between state of matter that we do not fully understand. But even that description might not be accurate, because there is a theory, one that has been gaining traction in recent years, that what exists deep inside Uranus is something even stranger. Scientists have proposed that under the right pressure and temperature conditions, water can transform into a state called superionic ice. In superionic ice, the oxygen atoms lock into a rigid crystalline lattice, like a solid. But the hydrogen atoms, instead of staying fixed in place, become liquid. They flow freely through the lattice of oxygen like a fluid. So you have something that is simultaneously solid and liquid at the same time. Part crystal, part flowing liquid. It behaves like neither a solid nor a liquid in the conventional sense. Laboratory experiments using extremely powerful lasers to generate brief moments of extreme pressure have actually produced superionic water on Earth. It glows black. It is dense beyond anything you would intuitively expect from water. And the researchers who created it believe it is almost certainly one of the dominant materials inside both Uranus and Neptune. If that is true, it would explain a great deal. The strange magnetic fields that Voyager 2 detected, with their offset and tilted orientation, could be generated by the movement of hydrogen ions through this superionic layer. The lack of internal heat could be related to how this layer inhibits the convection of heat from the deeper interior, and the utterly bizarre behavior of Uranus's atmosphere could be connected to the properties of this exotic interior material. But all of this is theoretical. We have no direct measurements from inside Uranus. Everything we think we know about its interior is inferred from models built on minimal data. An orbiter with a probe that could descend into the atmosphere and take direct samples would not just answer questions about Uranus. It would fundamentally expand our understanding of what matter can do under extreme conditions. It would connect planetary science to physics in ways that have implications far beyond our solar system. And it would help us understand all those ice giant exoplanets we keep discovering around other stars. This is the scientific argument that the Uranus mission advocates have been making for years, and it is a strong one. So let's get back to the timeline and what actually happened with ESA's role in all of this. After the 2022 Decadal Survey, ESA began formal discussions with NASA about potential collaboration on a Uranus orbiter and probe mission. These conversations were happening at multiple levels simultaneously, from working scientists discussing instrument packages to senior officials discussing mission architecture and cost sharing. There was genuine momentum. But there was also a complication that had nothing to do with Uranus directly. ESA had already committed its large mission slot in the near term to a mission called LISA, which is a gravitational wave observatory. It had also committed to a mission called Envision, an orbiter to Venus, and it was deeply involved in the JUICE mission, the Jupiter Icy Moons Explorer, which launched in 2023 and is on its way to the Jupiter system right now. These are all significant commitments. You cannot simply reshuffle them to accommodate a new flagship mission without consequences. The question ESA faced was not whether to go to Uranus. The question was how and when and in what role. Should Europe lead a medium-class mission to Uranus independently? Should it contribute a specific element, like an atmospheric probe, to a NASA-led flagship? Should it design a complementary mission that would work alongside the American spacecraft to do science that the NASA mission could not do by itself? Each option had different cost implications, different timeline implications, and different scientific payoff. What emerged from these discussions, which stretched through 2023 and into 2024, was a growing consensus around a particular model. ESA would not lead its own separate Uranus mission, but it would be a meaningful partner in a joint mission with NASA, likely contributing an atmospheric probe and potentially several of the scientific instruments on the main orbiter. This division of labor would allow ESA to participate in one of the most significant planetary science missions of the century, at a cost commensurate with a medium-class mission rather than a flagship. This is a significant reversal from the position that ESA had taken back in 2010 when it rejected Uranus Pathfinder. At that time, the implicit message was that Uranus was not worth the cost and risk for Europe. 12 years later, the message had changed entirely. Uranus was now considered worth it. The only question was how to structure European involvement in a way that was fiscally responsible. And the 12-year gap in between is exactly what this story is really about. It is not just a story about a space agency being slow. It is a story about how science priorities actually move and shift over time in response to new discoveries, new data, and changes in the broader context of what we are trying to understand about the universe. When ESA rejected Uranus Pathfinder in 2010, the exoplanet revolution was still in its early stages. The Kepler Space Telescope had just launched the year before and had not yet delivered the flood of planet discoveries that would reshape our understanding of what the most common types of worlds look like. The argument that Uranus was scientifically important because ice giants are the most common type of planet in the galaxy was not yet available to be made, because we did not yet know that was true. By 2022, it was one of the most established facts in astronomy. Over 5,000 confirmed exoplanets had been discovered. The statistics were unambiguous. Sub-Neptune-sized worlds, the ice giant category, were everywhere. They dominated the population of planets around other stars, and we had almost no idea how they worked. That is the discovery that rescued Uranus from the scientific waiting room. Not any new data from the planet itself, because we had not gathered any. It was data from thousands of other star systems that suddenly made Uranus look like the key to understanding a fundamental category of planetary architecture that appears throughout the galaxy. This is one of the most interesting things about how science works. Sometimes the most important data for understanding something comes from a completely unexpected direction. No one in 2010 would have predicted that the strongest argument for a Uranus mission in 2022 would be based on statistics about exoplanets discovered by a planet-hunting telescope. And yet that is exactly what happened. There is another dimension to this story that deserves attention, which is the question of what we almost missed. Launching a spacecraft to Uranus is not simply a matter of pointing a rocket in the right direction. Getting to the outer solar system efficiently requires something called a gravity assist, where a spacecraft swings past one or more planets to pick up speed, using the planet's gravity like a slingshot. For a Uranus mission, the most efficient trajectories typically involve a gravity assist from Jupiter. And here is the problem. Jupiter is not always in the right position to provide that assist. The geometry has to be right, and the windows when it is right do not come around all the time. The best launch windows for a Uranus mission using a Jupiter gravity assist open up during specific periods, and one of the best such windows falls in the late 2020s and early 2030s. If a mission is not ready to launch during that window, the next good opportunity could be a decade or more away. This is partly what drove the urgency in the 2022 Decadal Survey's recommendation. The community was not just saying that a Uranus mission should be the top priority in some abstract, whenever you get around to it sense. They were saying it needed to be the top priority right now because the favorable launch window was approaching, and missing it would mean a very long wait before the next one. That added a ticking clock to the entire discussion. ESA and NASA were not just negotiating the shape of a future mission in some leisurely fashion. They were doing so against a real deadline imposed by orbital mechanics that no one had any control over. For ESA in particular, this meant that the deliberate 12-year pause between rejecting Uranus Pathfinder and re-engaging with the concept had consequences. It had not made the problem go away. If anything, it had made the urgency more acute. The clock that was always there in the background had been running the whole time, and now it was louder. This is a genuinely important lesson in how the politics and logistics of big science missions work. The universe does not care about budget cycles or cosmic vision planning rounds. Planets move on their own schedule, and if you want to visit them efficiently, you have to be ready when the geometry is right. Now let's talk about what a Uranus mission would actually look like, because the details are fascinating and they help illustrate why this is such an ambitious undertaking. The current leading mission architecture, as developed by NASA's Jet Propulsion Laboratory and its partners, involves two main components. The first is an orbiter, a large spacecraft designed to enter orbit around Uranus and spend at least 4 years studying the planet, its rings, and its system of moons. The second is an atmospheric probe, a smaller spacecraft that would be released from the orbiter before orbital insertion and would descend into the upper atmosphere of Uranus, transmitting data back until the increasing pressure crushes it. The probe is in many ways the most scientifically valuable part of the whole thing. This is the instrument that would give us our first direct measurements of what Uranus is actually made of. What noble gases are present in what ratios? How much water is really down there? What the temperature and pressure profiles look like as you descend into the planet? How the winds behave below the cloud tops? These are measurements you simply cannot make from orbit. You have to go in. The precedent for this is the Galileo probe, which descended into Jupiter's atmosphere in December 1995 and transmitted data for 57 minutes before being destroyed. Those 57 minutes of data from the Galileo probe transformed our understanding of Jupiter and are still being analyzed and discussed nearly 30 years later. A similar probe at Uranus would likely do the same thing. It would give us 57 minutes or perhaps a little longer of irreplaceable data that no orbital measurement can substitute for. The instruments on the orbiter would include magnetometers to map the bizarre magnetic field in detail, mass spectrometers to analyze particles in the magnetosphere, cameras operating in multiple wavelengths from infrared to ultraviolet, radar for probing below the cloud tops, and instruments to study the rings and moons. Speaking of the moons, they are another major reason to be excited about a Uranus mission. Uranus has 27 known moons, all of them named after characters from the works of William Shakespeare and Alexander Pope, which is a wonderful quirk of astronomical naming conventions. The 5 largest are Miranda, Ariel, Umbriel, Titania, and Oberon. Voyager 2 flew past all of them in 1986, but did not have time to do detailed studies of any of them. What it did find was tantalizing. Miranda, the smallest of the 5 major moons, has some of the most dramatic topography in the entire solar system. It has a canyon called Verona Rupes that is estimated to be up to 20 kilometers deep, which is roughly 10 times deeper than the Grand Canyon. The surface is a bizarre patchwork of ancient cratered terrain and completely smooth resurfaced areas, as if different parts of the moon have completely different geological histories. Scientists have proposed that Miranda might have been shattered by a massive impact and then reassembled, with different pieces settling in different orientations. But that is just one hypothesis. We simply do not know. More recently, researchers examining the limited Voyager 2 data with modern analytical tools have found evidence suggesting that several of Uranus's larger moons, including Ariel, Umbriel, Titania, and Oberon, might harbor liquid water oceans beneath their icy surfaces. If that is true, they join a growing list of ocean worlds in the solar system that includes Europa at Jupiter and Enceladus and Titan at Saturn. And ocean worlds are interesting for a very specific reason. Liquid water, in contact with rock, with heat, over long periods of time, is potentially the kind of environment where life could exist, or could have existed. This is not a claim that anyone is making about Uranus's moons specifically, but the possibility is real enough that it is one of the stated science objectives for a Uranus orbiter mission. The moons alone would justify a multi-year orbital mission. There is enough science in the Uranian system to fill decades of research, but the planet itself remains the centerpiece. One of the things that makes Uranus so hard to understand from Earth, or even from orbit, is that extreme axial tilt we mentioned earlier. Because the planet rolls on its side, the seasonal changes it experiences are utterly unlike anything in the rest of the solar system. When we look at Uranus from Earth, depending on where it is in its 84-year orbit, we might be looking directly at one of its poles, or we might be looking at its equator, or something in between. Right now, we happen to be approaching a time in Uranus's orbit where the sun is increasingly illuminating its equatorial region after decades of pointing at the poles. This is creating changes in the planet's atmosphere that have been visible from Earth-based and Hubble-based observations. The atmospheric dynamics are shifting as the planet's seasons change. An orbiter arriving in the 2030s would be arriving during one of the most scientifically interesting periods in the planet's seasonal cycle. It would not just be observing a static world, it would be observing a world in the middle of a dynamic seasonal transition that only comes around every few decades. The timing, largely driven by those orbital mechanics windows we discussed, happens to be remarkably good for science. Now, there is one more piece of this story that has not gotten nearly enough attention, which is the human element. The scientists who have been pushing for a Uranus mission are not just doing so because they think it would be scientifically productive in the abstract. Many of them have been working on this for their entire careers. Some of the people who were early advocates for Uranus Pathfinder back in 2010 are now senior scientists who have spent 12 years watching their proposal be rejected, refined, championed, partially adopted, and gradually moved forward. Their careers have been shaped around this question in a very personal way. This is something that gets lost in the policy-level discussions about decadal surveys and mission architecture and budget envelopes. Behind all of it are individual scientists who have dedicated enormous portions of their professional lives to understanding a specific planet, or a specific type of planet, or a specific set of questions that only a mission to a specific place can answer. The 12-year gap between Uranus Pathfinder's rejection and the renewed push for a joint ESA-NASA mission is not just an institutional pause. For the people involved, it was 12 years of setbacks, of trying again, of making the case over and over to audiences that were sometimes receptive and sometimes not. There is a particular kind of resilience required to do big science at this scale. The timelines involved dwarf normal human career spans in many cases. A scientist who was in graduate school when Voyager 2 flew past Uranus in 1986 is now approaching retirement age. They have spent their entire working life waiting for a follow-up mission that is still not launched. When the Decadal Survey named a Uranus mission as the top priority in 2022, some of those people had been waiting for that moment for 35 years. That is not a number that is easy to sit with. But it is the reality of this particular branch of science, and it explains why the urgency in the community's advocacy has been so intense. The question of what Uranus can teach us is not just abstract scientific curiosity. For the scientists who have devoted their careers to this, it is personal. It is the unfinished business of an entire field. So where does all of this leave us right now? As of the most recent updates available, NASA is in the process of formally beginning pre-project studies for a Uranus orbiter and probe mission, working toward a potential launch in the late 2020s to catch the favorable Jupiter gravity assist window. The mission has been designated a priority project within the Planetary Science Division budget. Studies are underway to finalize the spacecraft architecture, the instrument suite, and the operational plans for a multi-year orbital mission. ESA's involvement is being worked out through ongoing discussions about the partnership model, with the atmospheric probe contribution being the most prominent option on the table. There are also conversations about European instruments being included on the main orbiter. The details are not fully settled, but the direction is clear. Europe will have a meaningful role in this mission. What has changed fundamentally from 2010 to now is the status of the ice giant question in the broader scientific community. Back then, a Uranus mission was one interesting option among many. Now it is the top priority for the largest and most influential planetary science organization in the world. That shift did not happen because someone at NASA suddenly decided Uranus was interesting. It happened because of a decade of exoplanet discoveries that transformed what the question of Uranus actually means. It is not just about understanding one unusual planet in our own backyard. It is about understanding the most common type of world in the galaxy. And ESA's reversal, from rejection to re-engagement over 12 years, tracks that transformation almost perfectly. There is something genuinely remarkable about the fact that the same scientific objective that was turned down in 2010 as too expensive and too risky is now being pursued as a top-tier priority, with multiple space agencies committed to making it happen. The mission did not change. The planet did not change. What changed was our understanding of what that planet represents in the larger context of everything we are trying to learn about the universe. That is how science works at its best. Not as a clean, linear progression from question to answer, but as a messy, complicated, sometimes frustratingly slow process in which the importance of a question becomes clear only when you have gathered enough surrounding context to understand what the answer would really mean. Uranus waited 38 years after Voyager 2 for a follow-up mission to be formally designated as a priority. The planet was always there, always strange, always full of mysteries that deserved to be solved. It just took us that long to understand why solving them matters not just for Uranus, but for our understanding of planets everywhere. When the Uranus orbiter finally launches, assuming it launches on schedule in the late 2020s, it will arrive at Uranus sometime in the late 2030s or early 2040s. Everything we send there will be built with knowledge that did not exist when Voyager 2 flew past. The instruments will be more sensitive, the computers will be faster, our understanding of what to look for will be immeasurably deeper, and the probe that descends into the atmosphere will transmit data that no one has ever seen before, measuring a substance and environment that might exist in a state of matter that we are only just beginning to understand even in the laboratory. The things we are going to learn will be extraordinary. The questions that data will raise will be even more extraordinary. And somewhere in those measurements, in those images, in those first close-up portraits of Miranda's impossible canyons and the shifting atmosphere of a planet rolling through space on its side, there will be answers that change what we think we know about this category of world. About how planets form, about how common they are, about whether the conditions for life might exist somewhere in that cold, dark, surprisingly complicated system at the edge of our solar system. That is what 12 years of waiting and 12 years of renewed advocacy was all for. And it is absolutely worth it.